Hello and welcome to Big Data section of architecture lectures. Data platform architectures that were designed 20 years ago struggle to solve the business problems of modern era with the exhaust of data, mainly because of social media and the amount of data that we started collecting. And that's how big data ecosystem evolved. Google provides fully managed multi-cloud analytics platforms to get insights while eliminating constraints of scale, performance, and cost. Composer, which is a workflow orchestration service built on Apache Airflow. Dataproc, it's a service for running Apache Spark and Apache Hadoop clusters. PubSub, it's a messaging service for event ingestion and delivery. Dataflow, so streaming analytics for stream and batch processing. Bigquery, which is the flagship cloud data warehouse from Google. Looker, it's a platform for BI, data application, and embedded analytics. Data Fusion, it's used for data integration for building and managing data pipelines. Data Prep, service to prepare data for analysis and machine learning. Data Catalog, which is a service for as a metadata solution for exploring and managing data. Now let's first look at Dataproc. Dataproc is a managed Apache Spark and Apache Hadoop service, which takes advantage of open source data tools for batch processing, querying, streaming, and machine learning. Dataproc automation helps create clusters quickly, manage them easily, and save money by turning clusters off when it's not needed. So if you look at to the bottom left, the Apache Hadoop ecosystem. Over the period of 5 to 10 years, Apache Hadoop ecosystem has become a very dominant force for lots and lots of data processing. It's at the backbone of Hadoop distributed file system, which is a distributed file system based on master slave architecture. And an HDFS cluster consists of name node and data nodes. And data is replicated across data nodes. By default, it's three for highly fault tolerant system. And if you look at each one of these open source projects, which has evolved over a period of time, is to satisfy specific use cases. So at the bottom you have the storage, then you have the primarily it's been yarn, which is the yet another resource negotiator, which is used for resource management. Then you have different capabilities in terms of how and what type of data that needs to be processed. So for in-memory processing, Spark, stream processing, Flink, Storm, Kafka, SQL over Hadoop, Hive, Drill, Impala, NoSQL database, HBase, search engine, Solar, data piping, NiFi, Flume, Scoop, machine learning, Madlib, Mahout, and Spark MLibs, scripting Pig, and then on the perimeter side, you have the coordination and management by which is mostly done by Zookeeper and Ambari. Then for security, you have Apache Ranger. Metadata management is from Apache Atlas. And for scheduling the jobs and everything, it's been using Uzi or Apache Airflow. Now, this Apache ecosystem has been evolving over a period of time, and every now and then new projects get added. So it's a very complex ecosystem. What where Google comes into the picture is that Google tries to abstract the need for infrastructure provisioning, cost management, and auto scaling capability. So a lot of enterprises they run their own version of Apache ecosystem tools, which is by setting up STFS cluster on-premise, installing all of these libraries, making sure they all work with each other. There are a lot of commercial products in the market, like Cloudera, Hortonworks, but Hortonworks and Cloudera have merged together. They have a lot of commercial offering, and at the same time, all of the cloud vendors have their version in terms of managed service for the entire big data ecosystem. Uh, so the question would be, why would you use Google offering when you could potentially just, these are open source softwares you can just install and configure it themselves. It's all about the administrative overhead and why data prop compared to open source or other cloud providers. The one of the most important thing you look at is the low cost. Dataproc is priced at only 1 cent per virtual CPU in the cluster per hour, on top of other cloud platform resources used. Dataproc clusters can include preemptible instances, and we talked about preemptible instances. So if you're running lots and lots of job and it's fault tolerant, even if one machine goes down, the other machines can pick it up. But at the same time, you will be paying very little price by using preemptible instances. Dataproc charges only for what is really used with second by second billing and a low 1 minute minimum billing period. It's blazing super fast. So without using Dataproc, it can take from 5 to 30 minutes to create a Spark and Hadoop cluster on premises or through IaaS providers. And if any one of you have, tried to set up entire big data ecosystem on on-prem or couple of servers, you know the pain of going through, navigating through each and every software, stitching them together so that your entire pipeline works. It's all integrated. Dataproc has built-in integration with other Google Cloud Platform services such as BigQuery, Cloud Storage, Cloud Bigtable, Cloud Logging, and Cloud Monitoring. So you have more than just a Spark or Hadoop cluster. You have a complete data platform. This is very important. If you weave or stitch together a cluster, you still have to work on integration patterns or integration channel with other tools. But as part of this ecosystem, Google provides a complete data platform. So not only you can do big data ingestion, big data processing, but also you can natively integrate with BigQuery, machine learning tools to to have that capability of complete data platform. Enterprise security, which is very important in terms of integrating it um, with SSO integration or um, sort of secure mode via Kerberos by adding a complete, natively integrated security configuration. Some of the most commonly used Google Cloud specific security features used with Dataproc include default at rest encryption, OS login, VPC service controls, and customer managed encryption keys. Containerized OSS job. This is very important because most of the big data ecosystem products are moving towards Kubernetes as their execution engine. So this Google Dataproc provides you a way to build your OSS jobs on Dataproc, which you can quickly containerize them with Kubernetes and deploy them anywhere, wherever the GKE cluster lives. So just to sum it up, it's to build fully managed Apache Spark, Apache Hadoop, Presto, and other open source software clusters. You only pay for resources you use and lower the total cost of ownership. Spin up an auto-scaling clusters in 90 seconds on custom machine, which is very, very, very significant. Encryption and unified security built into every cluster. It helps you accelerate data science with purpose-built clusters. Now, let's look at Dataflow. Dataflow is a managed service for executing unified stream and batch data processing that's serverless, fast, and cost effective, and is developed using the Apache Beam SDK. If you don't know about Apache Beam is an open source unified programming model to implement batch and streaming data processing pipelines that run on any execution engine. Now, if you look at the previous one, Dataproc, where you can set up the big data ecosystem, and then you have lots of tools to do the batch processing as well as stream processing. So you end up writing two different sets of code. What Apache Beam provides you is a unified programming model. So you can write the same code, which will work for batch as well as it will work for streaming data as well. And you can run that on any execution engine. And Google has actually leveraged this to build a serverless component to execute your batch data as well as streaming data. So this specific product has a lot of use cases, and I'll go through some of the use cases. But it's really important to understand it's one of the flagship products of Dataflow, which is completely serverless to do big scale data processing in the batch mode as well as in the streaming mode. So we talked about data processing pipeline. What is a pipeline? A pipeline represents a directed acyclic graph of steps. So a lot of times you will hear about the acronym called DAGs, and most of the big data native products have a DAG sort of a style of processing steps. Whether you look at Apache Spark or any other technology, so directed acyclic graph is a series of steps which itself leads to the next series to give you abstraction between different stages of data processing steps. It can have multiple input sources, multiple output sinks, and its operations, P transform, can both read and output multiple P collections. So in the Apache Beam world, uh, understanding the acronyms P transform and P collections is very important. So let me cover that first. A P collection represents a distributed data set that your pipeline operates on. The data set can be bounded, meaning it comes from a fixed source like a file, or unbounded, meaning it comes from a continuously updating source via a subscription or other mechanism. So in layman term, P collection is just a distributed data set. P transform represents a data processing operation or a step in your pipeline. So think of it as a any transformation you do, uh, it's a step, you know, and as part of that transformations, you do different kind of transformation. Some of the examples here are group by key, co-group by key, combine, flatten, partition, and is that step is basically termed as P transform. Now, if you look at the complete flow, and I want to get into the detail because data flow is really important from Google ecosystem point of view, is first thing first, you can use Apache Beam using Java SDK, Python SDK, and Go SDK. Now, when it comes to the input could be file-based, file systems, messaging, database, and other I/O services. So the example we're going to take here is a database table. Now, when uh, when any change happens, the pipelines have a trigger and way to collect data. So the triggers, which are the bottom ones here, they are classified as when to emit the aggregated result of each window. Now, what is window? Windowing is basically what portion of data till when, because the same it's a unified data processing framework. So the code works on batch as well as stream. So when it comes to streaming part of it, you need to provide a window which is from now until this time, grab the change records. So triggers and windows work hand in hand. Beam user triggers like event time triggers, processing time triggers, data driven triggers, composite triggers. And these triggers depend on the windowing capability. So windowing divides a P collection. P collection is just like a distributed data set according to the timestamp of its individual elements. So fixed time windows, sliding time windows, per session windows, single global windows, calendar based windows. So with the combination of trigger and windowing, you capture the exact set of data that you need to process. Then you will have a transform, which is a retransform, the exactly p transform. A retransform creates a distributed data set, which we call a p collection. We go to the next step and we do the transformation again, and that creates another distributed data set that we call P collection again. And then we write the transformed data into the output or into the sink. Now, the sink could be again anything file based, file system, messaging, databases, other input output sources. Now, we did talk about that when it does the P transform, uh, it can do a lot of different kind of transformation. One of them was Pardo. Now, Pardo is a beam transformation for generic parallel processing. The Pardo processing paradigm is similar to the map phase of a map shuffle reduce style algorithm. So, if you're aware of map reduce from Big Data World, uh, mapping was it's basically forking out and then you shuffle it back in to create the data set. Now that map is part of the processing, part of the transformational processing. So part do is equivalent of that map phase of map shuffle and reduce style algorithm. Now, this was more about the pipeline, and what where Apache Beam differentiates itself is it lets you use any of the runners. So there's an abstraction between the processing part of it, what operation needs to be done on the data, and where it needs to run. So what needs to be done is by following Apache Beam guidelines, and then where it needs to be run, you have a lot of flexibility to pick one of the runners. So direct runners run locally on the machine, great for, and this is where all of the developers, after they write Apache Beam code, is that they use the direct runner to use the native libraries of Apache Beam to run the pipeline. Alternatively, you can use Flink runner, Spark runner, Dataflow runner, Samza runner, Nemo runner, Jet runner, Twister 2 runner. So if you look at that, it's what Apache Beam is trying to do is trying to separate between what needs to happen with data and where it needs to run. And it gives you a lot of flexibility in terms of where it needs to run. And that's one of the main reasons this has come out as a completely serverless components because it's able to differentiate between these two characteristics of any data processing pipelines. On the bottom, you see a code sample creating a pipeline. It's import Apache Beam, and just like any libraries, you can import different things. And this example is in Python. What you do here is with beam.pipeline options, pipeline options as P, what you basically create a construct, a block, which determines what's going to happen as part of the transformation and collection and all of that. So this, you create a construct, then as part of the construct, you refer to the initial object that you created, P, and then you perform operations. Like in this case, it's creating a P collection by reading from text, applying transformation, which is again output P collection equal to input P collections after after transformation. So exactly coming back to this P collection here, you apply a transformation, you create another P collection. So you basically take care of the immutable nature of data as it processed through different steps. An example of the applying Pardue, the complex sort of algorithm, is you use a class where beam.do fun. Again, there's a lot of libraries which is part of Apache Beam. Once you start coding that, you will understand that is you define a process. You define a process which is more like a function. In this case, it is returning the length of the element, and then it's basically again word length equals to word beam dot pardo, which is coming back to this is input p collection is words. You applying a transform is compute word length, which is calling this function, and the resultant is another p collection. So it's a series of transformation that you put on a collection, you create a new collection, and that's how you navigate to the sync, the sync part of it. Overall, it's data flow is one of the premier and a flagship product that lots and lots of companies are using. If we look at some of the use cases, these are the two use cases I'll go through. Is the anomaly detection example. So in this case, there's a date. There's a lot of transaction data that's coming into cloud storage. Now you have a AI platform which is using the boosted tree model using TensorFlow, and it gives you a prediction based on the transaction. So what where you can use data flow is that you take the data from cloud storage, you put it into PubSub, then you stream the data out, and for each one of the transactions, you call the prediction APIs to to basically see whether it's a fraudulent transactions, and then you ingest that data or feed that data into BigQuery for much bigger analysis, and at the same time you can feed the entire transaction data to BigQuery. So data flow, because it's completely serverless in nature, you don't have to set up anything. You can plug in that data pipelining process using data flow. What the one on the right, if you look at any of the sort of edge-based application architecture, whether you have mobile, web, data stores, or IoT devices, they feed in the data, or they ingest the data through PubSub. PubSub receives that data. Then data flow streaming reads data from PubSub. It calls the AI platform to for the backfill reprocess. So based on the data that has come in, how it needs to be backfilled, and then you feed that data back into BigQuery and Bigtable as well at the same time for other analysis, and the data gets fed back into onto the edge network. So anywhere that there's a data processing required, data movement is required from different GCP services, data flow is a very good fit, and it has a native integration, and Google provides a lot of templates and deployment methodologies. There are a lot of Beam SDK scripts, uh, which gives you templates how to get data from PubSub and push it to BigQuery. You can automatically use all of them, those templates, and just insert your transformation logic, and you're good to go. So I hope this helps in terms of understanding where data flow comes into the picture. Uh, let's get to the next one, which is the Google PubSub. PubSub is an asynchronous messaging service that decouples services that produce events from services that process events. PubSubs offers durable message storage and real-time message delivery with high availability and consistent performance at a scale. So think of PubSub uh, as a decoupling service. So from stage A, you need to get to stage B, but you don't have want to have a linkage between them. So you decouple this process of delivering data, let's call it messages, is when you look at PubSub. So the core concepts of PubSub is basically to get data from point A to point B, but that linking service needs to be decoupled and it is completely managed service. So you don't have to worry about anything. You just need to follow through the framework to be able to emit data from point A and receive data at point B. So as part of the core concepts, it it has a concept of topic, which is a named resource to which messages are sent by publishers, which sits in the middle. Subscriptions, a named resource representing the stream of messages from a single specific topic to be delivered to the subscribing applications. So in the middle, we had topic. Now there's a subscription, which will determine where the message on the topic goes to. Then itself is the message, is the combination of data and optional attributes that a publisher sends to a topic and is eventually delivered to subscribers. Message attributes, which is a key value pair that a publisher can define for a message. For example, key INA.org language tag and value en could be added to message to mark them as readable by an English speaking subscriber. So if you look at the PubSub message flow, on the on the top, we have a publisher. Then they send messages to a topic. Topic could be stored somewhere. The topic has a subscription. Subscribers subscribe to the subscription. Once they receive the message, they send the acknowledgement back. So if I follow the sort of point A to point B trajectory is a publisher application creates a topic in PubSub service and sends message to the topic, which is this part. A message contains a payload and optional attributes that describe the payload content. The service ensures that the published messages are retained on behalf of subscription. So the published message is retained for a subscription, which is in some sort of message story. And then PubSub forwards message from a topic to all of its subscription individually. So you can have multiple subscriptions for a topic, uh, which is a very genuine use case that different people would like to receive the same message depending upon their use cases. Then a subscriber receives message either by PubSub pushing them to the subscriber's chosen endpoint or by the subscriber pulling them from the service. The subscriber sends an acknowledgement to the PubSub service for each received message that I have received the message and it can be deleted. So then the service removes acknowledged messages from the subscription message queue. If we look at so we understand the flow of message using PubSub. Now, in terms of the publisher and subscriber endpoints, that how they can send messages and how they can, in what different form they can receive messages. So, if you look at this one, uh, in the middle, as part of the PubSub, you have topic, and a topic can have multiple subscriptions. Topic can be sent by publisher through by many different channels. It can be sent through services, which is the GCP apps, third-party services, on-prem and legacy systems, or it can come through the front-end services, which is either triggered by IoT devices or end user apps in terms of mobile native and web content. So the different ways for publishers to publish that data to the topic. Now the topic and different subscription sit as part of cloud PubSub offering. Now the the subscribers can receive that data in many different formats. So one example is data flow or other processing service. So there could be an engine running which will keep listening to the subscription. So the moment the message receives arrives there, they take the message and send it downstream for processing. In this case, data warehouse, BigQuery, Hadoop cloud storage, or data replicas, Memcached, read replica databases, or search index, or you can have microservices components like VMs and containers, App Engine, or Cloud Functions receiving that message. At the same time, you can have a legacy or third party services, which is on prem, SEIMs, cross cloud, and all of them receive that message by using the SDKs. So publishers and pull subscribers can be any application that can make HTTP requests to pubsub.googleapis.com. Common use cases: balancing workload in network clusters. So for example, a large queue of tasks can be efficiently distributed among multiple workers, such as Google Compute Engine instances. Implementing asynchronous workflows. For example, an order processing application can place an order on a topic from which it can be processed by one or more workflows. Next one is distributed event notification. For example, a service that accepts user signups can send notification whenever a new user registers, and downstream services can subscribe to receive notifications of the event. Refreshing distributed caches. For example, an application can publish invalidation events to update the ID of objects that have changed. Logging to multiple systems. For example, a Google Compute Engine instance can write logs to the monitoring systems to a database for later querying and so on. Data streaming from various processes or devices. For example, a residential sensor can stream data to backend servers hosted in the cloud. Reliability improvement. For example, a single zone compute engine service can operate in additional zones by subscribing to a common topic to recover from failures in a zone or region. Google PubSub is one of the fundamental uh, capability for decoupling, message transfer or decoupling data transfer process between any source and anything. So it's a it's it's definitely worth putting a lot of stress on it. Google PubSub will be part of any big data architecture, any data processing architecture, any data platform architecture, any data ingestion architecture. So just give a stress on understanding Google PubSub. Next, we will look at Google Composer. So it's a cloud composer. It's a fully managed workflow orchestration service to author, schedule, and monitor pipelines that span across hybrid and multi-cloud environments. It's built on Apache Airflow, open source project, and it's operated using Python. Where does this fit in? Is if you look at the entire ecosystem, there's always events that needs to run as part of an end-to-end process, and that's where all of the orchestration process uh, come into picture. Apache Airflow is a very important part of big data ecosystem, which is it's a very stable and mature orchestration service. Google has built a fully managed workflow orchestration service on top of it. It's hybrid and multi-cloud, easy transition to the cloud or maintain a hybrid data environment by orchestrating workflows that cross between on-premises and the public cloud. Create workflows that connect data processing, and service across clouds to give a unified data environment. Think of Cloud Composer always as an orchestrator. It orchestrates different uh, functional areas into sort of one pipeline. Open source, it's built on Apache Airflow, so giving users freedom from lock-in and portability. Whatever assets or artifacts you have built as part of Cloud Composer, you can port it to any other cloud provider, any other service which has Apache Airflow, and you can run it from get-go. While Google is contributing back into, so Google is a very active contributor of Apache Airflow, and so that way it provides freedom from lock-in for customers as well as integration with a broad number of platforms, which will only expand as the Airflow community grows. Easy orchestration. Cloud Composer pipelines are configured as directed acyclic graphs, DAGs, using Python, making it easy for any user. One-click deployment yields instant access to a rich library of connectors and multiple graphic representation of your workflow in action, making troubleshooting easy. Automatic synchronization of directed acyclic graphs ensures jobs stay on schedule. So, like we said, it's an orchestrator. It's the same as Jenkins or any of the orchestrating tool in the market. So all mo- all of the orchestrating tool basically depend on connectors to to be able to connect to different functional areas, and that's where Apache Airflow, because it has a very wide community, it excels because it has pre-built connectors and there's a rich set of libraries. If you look at the basic Airflow architecture, uh, as part of Apache Airflow, and this is taking the persona of a data engineer, um, there's a configuration file called airflow.cfg, and then it has a very sophisticated user interface. And then web server schedulers and workers, they all connect to metadata DB, and the pipelines are designed. The Python code is defined as DAX, which is just a series of steps. So metadata database, it stores the metadata about the data pipelines that's being run. Uh, m- Postgres is pretty famous with Airflow as a metadata database. Then you have the web server and scheduler. The Airflow web server and scheduler are separate processes run on the local machine and interact with the database mentioned above. The executor runs within the scheduler. So if you look at any orchestration platform, you have the configuration, you have a metadata database, then you have the web server component for the user interface, then you have an scheduler component, and then you have the actual workers which actually execute the jobs using connectors. It's exactly the same pattern. Airflow CFG is the Airflow configuration file, which is accessed by all of them. DAG refers to the DAG files containing Python code, representing the data pipelines to be run by Airflow. The location of these files is specified in the Airflow configuration file, but they need to be accessible by the web server, scheduler, and workers. Now, let's uh, let's try to summarize what we have looked at is the how Google makes big data ecosystem possible, how it helps you make data processing as a unified data processing serverless, then how it decouples the transport of data, and then Composer, which is basically how do you create that orchestration layer to execute your jobs across different capabilities that Google Cloud Platform provides when it comes to big data ecosystem. Just adding on to this, we will look at Cloud Data Fusion now. As the next topic, let's look at cloud data fusion. Cloud Data Fusion is fully managed cloud native enterprise data integration service for quickly building and managing data pipelines. It's powered by the open source project Cdap. Uh, if we follow the pattern for big data, there's there's a lot of integration challenge in terms of the whole big data ecosystem. So where data fusion comes into the picture is in terms of doing providing an abstraction between the big data processing framework to the underlying infrastructure. And let me get deeper into this. The this the CDF, the web UI, it's basically used to build a scalable data integration solutions to clean, prepare, blend, transfer and transform data without having to manage the infrastructure. And it uses ephemeral or existing data clusters to execute the pipeline. So to understand this in much greater detail, let's concentrate only the left side, which is the anatomy of a big data application. What does a big data application require? What does it mean developing a big data application? Is primarily following things: data collection, data exploration, data processing, data storage, and data serving. So if you look at that, this is more about how the data needs to be prepared for consumption. It's as simple as that it is. But the way this is done in a big data ecosystem is that not only that requires a very significant amount of knowledge of where that this process runs, how it runs. What CDAP tries to do is abstract that process, is that you only worry about the data processing frameworks but you don't worry about where and how it runs. So if you look at the stuff in the middle here is the basically CDAP abstraction is you have the entire Hadoop stack with all the tools and everything, and then you have the application abstraction and data abstraction, which is I want to do something with the data. I don't care how it is stored in SDFS, how different components are actually executing it. Uh, all I care about is that I should be able to drag and drop and do the data manipulation, which creates intermediary data sets, and I should be able to just go and run it. That's exactly where Cdap as an open source is gaining a lot of ground. Is a Cdap application. It consists of following components primarily. The programs that you write to do the data processing, whether it could be MapReduce, Spark, and all of that. What it creates is the data sets for data storage abstraction. It doesn't care how that data is stored, whether that data, where it's storing, it's immutable, or whether it can't support ACID. It doesn't care about all of that. It's completely abstracted. And the serving part of it, how the data is integrated with other players, whether using JDBCs, querying RPCs, and all of that. So as a result of this, what CDAP provides is a code-free, self-service, UI-driven data integration tool. And this resembles with a lot of data integration tools that we used to have back in the day, uh, from Informatica, IBM Data Stage, and Talent, a lot of other data integration tools. CDAP provides you a self-service UI where you can drag and drop different services, drag and drop the transformations, and it will automatically take care of running it on either on ephemeral clusters or on data prop clusters, which supports the entire big data ecosystem tools. It integrates with Google's big data tools, storage, Dataproc, BigQuery, Spanner, etc. It's an enterprise-grade security, metadata and lineage integration, built-in connectors for modern and legacy systems. Now, let's look at data catalog. So, we went through the process of how the data pipeline and data processing needs to happen. One of the very important aspects of to be able to search the data that you are processing or that you have stored. So that's where Google Data Catalog comes into the picture. It's a fully managed and highly scalable data discovery and metadata management service. Pinpoint data with a simple but powerful faceted search interface. Sync technical metadata automatically and create schematized tags for business metadata. Tag sensitive data automatically through cloud data loss prevention integration. So in this particular example, through all of your data processing, data pipelines, you know, you have data in BigQuery, PubSub, and cloud storage. Data catalog connects to all of these different services. Um, and it it gives you a ready to use sort of a, a powerful interface where you can search on your data, you can tag your data, you can do a very faceted search. It also provides ready to use open source connectors for all of the on-prem based or MySQL, Postgres, Teradata, Oracle, SQL Server, Redshift, and a lot of this. It's truly multi-cloud in nature. Key feature, it's serverless, fully managed and scalable metadata management. So it requires no infrastructure to set up or manage. Metadata as a service. Now, this is very important. The data governance teams across all organizations, they have struggled to understand the metadata of the data that they are ingesting. And this has been one of the biggest use cases for regulatory requirements where they need to understand what the data is about in terms of sensitive information, tagging of the data. So Google Data Catalog service is really, really important because it's serverless and it lets you connect to all of the all of the data repositories. It's a central catalog, a flexible and powerful cataloging system for capturing both technical metadata as well as business metadata. Search and discovery, a simple and easy to use UI with powerful structural search capabilities to quickly and easily find data assets, powered by the same Google search technology that supports Gmail and Drive. So there are a lot of products in the industry which only specializes in search and discovery of metadata. So having a data catalog as part of Google ecosystem and completely service takes away a lot of the heavy lifting that that you need to do in terms of using any of the other commercial products. Schematized metadata supports schematized tags um, in terms of different type of data tags, not just simple text tags, providing organizations rich and organized business metadata. It has a cloud DLP integration, which is one of the uh, important characteristics is discover and classify sensitive data, provides intelligence and helping to simplify the process of governing data. It's got on-prem connectors, so you can ingest technical metadata from non-Google Cloud data assets, because that's what data catalog is about, to have the unified view of all of your data assets. It has a native cloud IAM integration and the governance, which offers a strong security and compliance foundation with Cloud DLP and Cloud IAM integrations. Now, with this, let's move on to the next one, which is Cloud Data Prep. Now, Cloud Data Prep it's uh, it's owned by a third company called Trifacta, but it's integrated within the cloud Google Cloud ecosystem. Cloud Data Prep by Trifacta is an intelligent data service for visually exploring cleaning, and preparing structured and unstructured data for analysis, reporting, and machine learning. Think of data prep as one of those profiling tools that we used to have in the industry, whether the IBM Information Analyzer, or there's a lot of profiling tool from Informatica. There's a lot of different third-party profiling tools, which lets you visually explore and clean and prepare data. Why this has become more important is if you talk to any of the machine learning engineers, most of their time they spend understanding data and cleaning data. Applying a machine learning model becomes much easier, but if your data is prepared well. Um, so that's why cloud data prep, because it has the visual exploring and cleansing capability, it's really handy for machine learning and advanced users who don't really want to swim through the complexities of programming language and cleaning the data. So in terms of its architecture, it can ingest data from anywhere, BigQuery storage, sheets, Microsoft Excel databases, applications, and all of that. You can use data flow to move that data to BigQuery or cloud storage for further analysis and ML. So in this particular example, when I was giving an example of a machine learning engineer, is basically they can use the cloud data prep to explore it, clean it, and then feed it into cloud AI platform where they can apply their machine learning algorithms to get the insight that they are after. It has a overall governance and automation in terms of data cloud, cloud functions, and cloud composer. The features of cloud data prep, it's a serverless simplicity, and this is very important when it comes to Google Cloud Platform services. Not to worry about managing services, not to worry about uh, what sort of servers or what sort of capacity these things need to run, depending upon the data. Google takes care of that automatically. Fast exploration and anomaly detection, pattern matching and standardization, data standardization. If you work with the um, regulatory work or the industries which are highly regularized, and also if you look at if you work in the industry where you deal with a lot of customer data, the the data standardization, data matching, uh, and the whole survival shape of data based on data matching is very important. So a visual display of exploring that data, it's a very handy tool. It does active profiling and sampling. It integrates with Google Cloud Platform. It does the data pipeline orchestration, and we saw this example for data flow, picking it from Cloud Data Prep and pushing it to other services. Data quality rules, again, um, data quality is a very important part of cleaning the data, enterprise scale operationalization, and advanced security. So, if again go, going through the topics that we have discussed, cloud data prep uh, is a very important step in terms of analyzing, profiling that data, applying data quality rules, doing the matching of data, and have that data sent to different services for advanced analytics or deeper insight. The cloud data prep plays a very important role. Now let's look at Looker. Looker is an enterprise platform for business intelligence, data applications, and embedded analytics. We have gone through the big data ecosystem, how the data needs to move through, how the data needs to be prepped. Then the last step is always is the BI, an analytics platform which can draw those shiny dashboards and provide you analytics in a way which um, you know majority of stakeholders can consume. It's an integrated end-to-end multi-cloud platform to connect, analyze, and visualize data across Google Cloud, Azure, AWS, on-premises database, or independent software providers SaaS applications with equal ease at high scale. As you can see here in example, different sort of ingestion methods. They all ingest data through different uh, technologies, and we have discussed about most of these. Then it comes to Looker platform, which is a full-blown platform. It has a security authentication, Git version control, semantic data model, solution accelerators, Looker APIs as well, and then you have a capability in terms of developer SDKs and different ways to build with data. Uh, the Looker, apart from having this shiny dashboards, ad hoc data exploration, uh, manage schedule and alerts. You can also browse saved content. It also helps you do data activation. That's by triggering SMS, emails, Slack channels. So if something has happened, so it goes way beyond just the standard BI application. And it also does the data delivery in terms of webhook, email, or PDF. So think of a scenario when, depending upon all of the analysis, data gets fed into Looker, which has a dashboard created, alerts created, and if it has reached some certain threshold, it needs to send out some triggers and as well as notify concerned people. All of that is part of this. Now let's look at BigQuery, and we have discussed about BigQuery. So BigQuery is, you know, ideally database, but it plays a very important role in big data ecosystem. It's a Google Cloud's fully managed petabyte scale and cost-effective analytics data warehouse solution. With BigQuery, there is no infrastructure to set up or manage. It's completely serverless, and that's what differentiates BigQuery from all of the other data warehousing solutions like Redshift, Snowflake, Azure Synapses. It's a database service which has primarily two parts: storage service and the query service. As part of the storage service, you have a realm of project, data sets, and table. So you organize your data in terms of table, then the data sets, and they all sit under a project. The data, which is part of the tables, sits in a Google native file system called Colossus, which is highly compressed. On the BigQuery query service, it gives you different ways to query data uh, through web UI, BQ, REST APIs, REST API calls, and it also has connectors to a lot of other services. The most important thing is that these two services are connected through a petabit network, which is the same network that Google uses for most of its world famous services. Now, apart from this, you know, there's there's a lot of different key features in terms of BigQuery ML, which is to be able to write machine learning or use machine learning algorithms using SQL language. BigQuery GIS is the geospatial analysis. BigQuery BI engine, which helps with the BI analytics. Connected Sheets, you can use Google Sheets to interact with BigQuery and to be able to process large amount of data from the familiar pivots, functions out of Google Sheets. It's pretty outstanding. Now, the sort of next generation is the BigQuery Omni, which is still in private alpha. It was announced recently. BigQuery Omni provides you capability to connect to different cloud data warehouses and provide you an sort of aggregated and centralized view of your data. So it can connect to Redshift, it can connect to Azure, it can connect to on-prem cloud database warehouse solutions. That gives you very, so it's a common interface to be able to connect to all of the data warehouses. So now that we have looked at all of the big data solutions, let's look at some use cases and how all of these come together. And remember the journey that we have gone through is understanding the big data ecosystem, understanding different data pipelines, understanding how you can orchestrate things, understanding how you can help in prepping that data, then understanding how you can get insights from that data. So if I take an example of data warehouse modernization, which is to solve today's most challenging demands and seamlessly scale businesses with advanced and multi-cloud capabilities, BigQuery is perfect for that use cases with its BigQuery ML and GIS services. Business intelligence to reveal the true power of your data and bring clarity to every situation with Looker and Google Cloud. So you can use Looker, BigQuery BI engine, connected sheets, which can connect to BigQuery to query against massive data sets. Google Data Studio, which is part of Google ecosystem, but not a Google proprietary product, which is a very simple BI tool. Workflow orchestration to author, schedule, and monitor tasks across hybrid and multi-cloud environments with the familiarity and portability of Apache Airflow. Uh, we've talked about Cloud Composer, Cloud Functions, and there is a new product coming up, which is still in beta, is Workflows. Data Lake Modernization uh, to empower your teams to securely and cost effectively ingest, store, and analyze large volumes of diverse, full fidelity data. BigQuery, Dataproc, cloud storage, marketing analytics, Google Marketing Platform, Data Studio, BigQuery data transfer services. Data security and governance is a very important part of it. Data catalog, we talked about, which helps you search your technical as well as business metadata. Cloud DLP, we look at it during the security section. And then Cloud IAM, which has a native integration in terms of security and governance. Stream analytics, the to ingest, process, and analyze event streams, of course, you can use PubSub to decouple the message transfer services. You can use Dataflow to ingest that data from PubSub, and you can use BigQuery to push that data into BigQuery for for deeper insights. Data integration, cloud data fusion, so is to have a cloud native service for efficiently building and managing ETL and ELT pipelines. So this brings us to the end of um, big data lectures. We talked about a lot of tools, but it's very important to understand the whole journey of uh, how data traverses for any application, and you categorize it based on data ingestion part of it, uh, data transformation part of it, data insights part of it, and the backbone of all of it is the the execution engine. And that's where, we have tried to navigate through these sections with different products, and where Google provides the most capability is that most of these platforms are managed platforms. So at the end, you're only looking at doing the data processing work rather than worrying about infrastructure. So I hope this was useful. Thanks, thanks for listening. I'll see you in the next lecture. Thanks.